Hi, quite a while ago I did a teardown of this Lecroy 9384C 1 GHz oscilloscope, 4 gig sample per second, and if you haven't seen it, I'll link it in down below. Check it out first if you haven't done that. And as you would have seen in that video, this thing had a few issues and it had a fault, and I haven't really had time to look into this thing at all. I just checked the power supply rails and they were all fine at the time, and well, just the other day I decided to crack it open again and have another look. So this is going to be an attempted repair video, and I say attempted because I have no idea if I'm going to be able to fix this thing, find the problem or whatever. So if you get to the end of this video and I haven't fixed it, tough luck. All right, so this is like a real-time repair, because I just powered this thing up, and once again I measured the voltage rails again, had the same fault as before, and the voltage rails were all fine. And let's have a look at it down here, and it was all fine. So I cracked it open and then I started to run it again, and I was about to turn on the camera and start troubleshooting the thing, and then I found it just it just failed. It switched off. I heard a bit of a sizzling sound or something like that. Maybe it was my imagination, I don't know. It didn't sound that great anyway. And let's have a look at what I found. If we get our, here we go, get our multimeter here and look at this. Let's have a look. And here's the power. Here's the power supply here. It normally sits on top. All this metal work, as you saw in the teardown, all normally sits over the top of this. I got it off, and it's got multiple rails. It's got 3.3 volts there is the yellow one. The orange one down in there is 5 volts. There's 4 of those, or 3 of those. There's ground. There's plus minus 15 volts. There's plus minus 2 volts, and a couple of other voltages there as well. And I think there's some sort of sense line as well coming back. But after I heard this sizzle and it stopped working, I measured the rails again, and the 3.3 volt rail is dead. So I've got it on ohms, and if we have a look here, let's probe our 3.3 volt rail. Look at that, 0.17 ohms. Let's zero out our test leads, because this is a very low, we're getting about 61 milliohms there. So let's zero that out. There we go, and that is repeatable. There we go, nicely repeatable, down to plus minus 1 milliohm. I like it. And let's probe that again. That's our 3.3 volt rail, folks. Just over 0.1, or let's call it 0.11 ohms. And obviously it shouldn't be that. And let's swap the polarity around just in case it's some sort of semiconductor junction or something like that. No, it is spot on. It's 0.11 ohms. So something on this thing has shorted out, and I didn't measure the resistance before this happened, of course, but that is definitely not right. Something is completely shorted, and we're getting nothing on that 3.3 volt rail now. So the power supply is shutting down. So woohoo! Excellent. This is what you're hoping for with a repair. You're hoping that, you know, a power supply like this will fail. At least you've got something to troubleshoot. So well, we're going to have to try and find the short on this thing. In theory, it could be like a power plane in the middle of the board or something, but it's more likely to be a cap or a component. But I have no idea how many caps and how many chips are in parallel on that 3.3 volt rail on here. I'm assuming like maybe all of the memory up here, and a lot of the ASICs and stuff like that, and a whole bunch, probably all the processor board. So let's start. We've actually got some things which we can unplug. So we've got the processor board here. So let's whack this out and measure that again, because you always start with the stuff that you can, no, 0.11 ohms. You always start with the stuff that you can physically remove. And if you've got a couple of modules like this, there's the memory module there. I don't know, can't see any signs of visual, the first thing you look for is going to be visual stuff, but we're not into the visual inspection yet. We're just removing these modules, see if we can localize that short. So I hope I've got time to fix this today. I've only got an hour or so before I've got to head back babysitting little Sagan. So it's not that one. There's nothing visual on that board that I can see at all. Let's measure it again, and I don't like our chances. No, bummer. It's somewhere on this main board. Murphy, every time Murphy will get you. So looks like we've got to pop out this main board, which is a mongrel. Got to undo all the screws on here, lift it all out. So let's give that a go. You've seen the bottom. If you've seen the teardown, I won't bother taking off all this metal work yet, because yeah, we can, you know, start with the power connector up here and work our way around the board. Now, I have no idea if this fire is related to the original fault. So this you're short on the 3.3 volt rail is in any way related to the problems I was getting with the scope, all those waveform corruptions and all that sort of stuff. It certainly could be, because if you saw the previous video, you'll notice that the way it was kind of sort of working, it was sampling a sine wave, but the memory was being all corrupted and stuff like that, or it appeared to be. So that could certainly be something to do with the digital 3.3 volt rail. So I'm hoping that whatever was causing the problem on the 3.3 volt rail before, it could have been excess ripple or, you know, some other issue like that, was loading down the rail and it was still working, but then it eventually failed and went kaput, and the magic smoke escaped, and now it's completely failed. So I hope they're related, but Murphy might intervene again and ensure that they're not related, and this 3.3 volt is a new fault. So even if I find this 3.3 volt issue and I fix it, there's no guarantee that it's going to fix the original fault. But fingers crossed. Now, when you're tracking down this sort of short on a board, you want the greatest resolution possible on your multimeter. Now, this is a case where accuracy does not matter. You just want resolution, because we don't care if it's 5% accurate, 10% accurate, or 0.005% accurate. We don't give a toss. All we care about is the resolution. So let's take the Fluke 87 in regular 3.5 digit mode. Okay, we put it on ohms, we short it out. We've only got a lousy 100 milliohms resolution there. It's absolutely hopeless, right? And you saw that our short on this board was 0.11 ohms. So how can we trace this fault down to a lower and lower resistance with that? You can't. You at least need an order of magnitude better, at the very least. So we put it in 4.5 digit mode and we get an extra digit of resolution in there. So the Fluke 87 in 4.5 digit mode like this, yeah, we're going to see that last digit, but you know, it's not as good as it could be. Ideally, you want like a 5.5 digit meter, for example, or something like this Agilent 1272A, which has a 50 ohm mode instead of the usual 500 or 200 ohm mode. So you short it out and bingo, we got 1 milliohm resolution. So that's brilliant. So that's what I'm going to do. And of course, you saw before, we've got 1 milliohm resolution. Fantastic. This is what you need for tracing down a short on a board like this. Or you could use like a bench multimeter or something, you know, if you've got like a 5.5 digit bench multimeter or something like that, that'll do the job as well. So we know it's not either of our other boards, it must be on this main board. So here it is again, and there are 3 pins. These top 3 pins here are all the 3.3 volt pins. So if I get in there and get the third pin down, there it is. Now round about 0.11 ohms, and then the next pin up, also 0.11 ohms, and the next one up is open. That's my finger there. It's my fingers on the probe doing that. So that top one is open. So it looks like that top pin, which is very surprising, because usually that they're all shorted together on the board there, and they're just using the 3 pins to get extra current handling capability through that. I mean, the 3.3 volt one isn't the highest current supply on this board. I think it's the 5 volt, because it's got 4 wires on it. So usually they short them all together to an internal plane or a internal track. But let's flip this thing over and have a look down here at what we've got on these pins. Now, it's often handy to know how many layers this board is, and often, well, a well-designed board a multi-layer board will have these layer designators here, and they're actually physically copper, and they've placed them on the different layers like this. And this one here, you can see number 1 is placed on, well, layer number 1, the top layer, and then layer number 2 is under that, and then 3, 4, 5, and there's actually 6 there if you flip the thing over, because it's physically on the bottom layer there. So there it is. It's upside down there, but you can see 1, 2, 3, 4, 5, 6. So we've got 6-layer board here. And as I said, in theory, the short could be on the internal layers on the planes, but usually that doesn't happen as a post-manufacturing fault. Usually it happens at the PCB manufacturing stage. Now, these are the 3 pins we're concerned about here. They're shorted to ground somehow, and I can't see those pins coming out on this top layer anyway to any sort of big beefy power track at all. So clearly they're not connected on the top layer here. So we need to flip this thing over and have a look at the bottom layer. And here's the bottom layer, and here are the 3 pins again. And once again, bummer, they're not connected through to this plane down here at all. But this is, this is more of a manufacturing type inspection, really, because you wouldn't expect a working unit to suddenly fail and then to find a short on your PCB. It's got to be almost certainly with inside one of the components in parallel. But in this case, it's going to be next to impossible to follow this rail, because it physically follow it 2 components, because it just goes off to an internal power plane somewhere, which probably snakes across the board. They might have a whole plane in there dedicated to the 3.3 volt rail, and another one dedicated to the 5 volt rail, for example, and then the other power rails, or it could be a split internal power plane or something like that. So that's why you need these multi-layer boards, because this power has to go everywhere. Now, I don't really have the exact schematic for this thing. I've got a schematic for the M model unit, which isn't exactly the same, and it's very difficult to read. So really, I pretty much, we're going to do this without the manual, because and finding the designator components anyway of all the components on the 3.3 volt rail. What we're just going to do now is just probe around. Well, first we'll do a visual inspection, of course, first step, to see if there's any obviously blown components. But I've had a quick glance over it, I don't think there is. So next we're going to actually trace this thing down and try and hunt down that value as it gets lower and lower towards the point where it's ultimately shorted. So with a 1 milliohm resolution meter, we should be able to do that fairly well, because any sort of short fault on a product, or any sort of product like this, 1 milliohm resolution is generally going to be enough to find, to narrow down that resistance reading and eventually track down the fault. Now, I've taken off the metal shield on the bottom here, and I'm looking around and I can't see any components that are visually gone. Of course, the thing you're going to look for most often is the cap. So you're going to look for these tantalums here, make sure they haven't blown. I don't know if they're across the 3.3 volt rail yet. Odds are at least one of them in each of those channels is, I would be guessing. And well, I can't see anything obvious there. And likewise, on the top of the board, we really have to scan this thing over and see if we can find any shorts at all. There's a couple of tantalums down there. We've got a couple of big electrolytics here, and there's one over there. There's a couple of electrolytics there, but there's a whole bunch of little tantalums on top on the analog rails. And no, I had a good look over this board, and I checked for both the tantalums, the electrolytics, and other caps, and I can't see any that have visually failed, i.e. melted, have a big burn hole in them or anything like that. So the next thing you're going to look for is the ICs themselves, because ICs do actually fail and go short internally. It's not that uncommon, and generally you would look for like a burn mark in the center of the chip, or it's, you know, it's indented or warped or something like that, because that's what, like if the die inside is heated up and it's, you know, you've got SCR latch up or something like that. I've done a video on SCR latch up, which can cause failures like this, permanent failures within the chip, then or some other failure mode, of course, then you'd expect to see a visual deformity in the chip if it got bad enough, but not always. Murphy will ensure that the fail will be inside the chip with no visual no visual outside clue at all that anything's gone wrong. So you're looking for little ripples or cracks in the tops of the chips, or little indentations or bubbles or something like that, or a big gaping damn hole in the thing perhaps. But I've had a fairly good look over this thing and I can't see anything. What a bummer. So we're going to have to start tracing this thing down with the multimeter. So let's start tackling this thing. Here is our 3.3 volt rail up here. You remember it was that second pin down there. By the way, the other thing you're going to need is very sharp probe tips, very high quality sharp probe tips to pierce the oxidization on the solder joints and get right into those solder joints, so you get the lowest resistance reading possible, because you don't want variation. When you're chasing a delta variation in a contact resistance like this, by delta I mean a difference, we're starting out with 0.11 ohms here, and we're going to measure the differential as we go across the board. So we're looking for the difference. So repeatability is a key thing. So if these contacts are all dodgy and or you're not putting enough force on there, you don't want to get dodgy readings. And we're talking very low resistance values. But as you can see, this thing is quite repeatable. As we saw, like you short it out like that and it's 0.06. So ultimately, when assuming that we find our short, it's going to be around 0.06. If we get down right to that, then we can, you know, zero out the probes maybe and even track it, do some fine tracking right at the final point. But you know, it should get down, so we should trace it from 0.11 down to 0.06, and we can at least localize the area where the fault is going to be. So contact resistance, absolutely key. Nice firm pressure on there. So let's take a look. We've got our this is our 3.3 volt rail. So let's go between the ground pin again. There it is. Hey, there we go, 0.16. Oh, look, it's going all over the place. Look at that. Oh, I hope it doesn't disappear on us. I've had that happen once or twice where I've been tracing the thing down, then it suddenly vanishes, and that's when you're really having a bad Murphy day, let me tell you. So, oh, it's gone up to 0.17 now. So, you know, maybe you'd give this is where you'd probably give the board a little bit of a flex to see if it's some sort of flexion issue, like a physical issue within the component. So I'm flexing the other side here. No, it's not. I don't see any drastic change there on the board. So 157 ohms. Okay, well, let's just skip on over here to these caps. I reckon one of these has got to be the 3.3 volt rail. I'd be a bit surprised if it wasn't. No, there we go, 136 ohms and climbing. That's another rail. You know, we're obviously charging up the rail capacitance there. And of course, if you swap your leads around like that, you'll no doubt get something different. There you go. So yeah, don't follow that. That's a red herring. So let's have a look at this cap here. Hey, bingo, there you go, 0.162. So technically that's higher than what we had. So there you go, another rail. So that cap there, we've at least got one of those caps, as I said, on that rail there. So we'll find that one of these caps, it's slightly laid out different here, but like this one over here will be possibly, yeah, 0.16. They're all slightly different layouts, these boards. 52 ohms, Yeah, so, all right, let's probably start probing some caps on the top and see. I mean, we're getting a reference point at this connector down here, so let's measure sort of something right on the opposite side of the board, shall we, and see if that makes a difference. So if our power connector's over here, let's try and get something like right over in this trigger section over here perhaps. So maybe not. I mean, it's not a definite, but I don't know, you'd assume that they'd, maybe not in the trigger section, maybe that's not, no, it doesn't look like that might be the case. But what about these little puppies down here maybe, although these look like local regulators, so we might be now at 2.7 ohms. Now I've had a quick little probe around these ASICs. You can see these four large ASIC ADC hybrid modules here in the circuitry on the back. They've got no bulk decoupling on there, just lots of small caps, and I've probed quite a few of those and I can't seem to find any 3.3 volt rail on there, so that hybrid doesn't seem to use any 3.3 volt, which is not terribly surprising. But these other ASICs or whatever they are under the heat sinks, I haven't got the heat sink off to look at the number on there, that we looked at before, we can actually certainly trace those. So let's start doing that. I mean, once again, our reference point over here, 0.152 ohms, 0.151. I'm giving the board a bit of a flex there with my arm at the same time, which you probably can't see, but 0.152. Let's go across to the cap here, 0.154. You see how it's higher? I mean, we're talking, 2 milliohms higher there, but that is enough to tell us that it's closer towards here than it is here, that extra resistance. Now if we go over to here, we should see slightly higher. So I'm assuming, so if this one is 0.157, let's say, and if we go, if we know this point over here is lower, this one's higher, then something over here should be higher again, or over here should be higher again. So let's find the cap in there. I've got this on manual ranging now, by the way, just so it doesn't have to auto. Oh, hang on, 0.24. I'm probably not probing that thing right. There we go. No, look at that, it's lower again. That's quite interesting. It's lower, 0.148. Very, very interesting. It's higher over here. So this is now our lowest point. This is interesting. Let's go over here. 0.154. And I'd expect this one over here to be higher. Oh, look, it's changed. It's lower again. Has it changed? Yeah, look, I'm putting, actually that could be the solder joint. Although the others, I was putting a lot of pressure on that, 0.16, but you saw it go down before, just a second ago, to like close to 0.1 again. Put a bit of flexion on the board with my arm. No. Oh man, this is, I was hoping this would be a good demonstration of troubleshooting this thing, but it seems to be all over, like tracing down a classic short on a rail, but it seems to be all over the shop. Oh, this is annoying. I just did that again off camera, and once again it went down to 0.11 ohms. I swear it did, and now it's back up. As soon as I press record, it's the white coat syndrome. As soon as the people in the white coats come around, the fault disappears. That's a classic industry term. So I'm going to actually mark these ones with red, so I can come back to them. That's the only one in that channel, so I don't have to dick around again. The ceramics in there as well are also across the 3.3 volt rail. So there's a whole bunch of caps in there, but it's, if it is one of the caps, it is most likely to be one of the tantalums, you would think. It doesn't necessarily have to be in this section. I still haven't fanned out over the board or anything like that. I'm just trying to get a reference point at the moment. I find it hard because this one here keeps jumping around, but it could certainly be. That could be a telltale sign that it is actually that cap. And, well, I don't want to be a bit premature and go sucking it off and doing that yet, or maybe that could be a smart move. I mean, you know, it could certainly be one of these chips which has failed. Who knows? Because we can't visually inspect that because these heat sinks are glued well and truly onto this thing. I don't think the 3.3 volt is going into one of these ADC hybrids, so that doesn't look to be a problem, but there's no bypass caps on the top really, so it all seems to be, all the action appears to be on the bottom. You know, there's no reason I targeted this area first other than the fact that I know it's digital, because here's all the analog part of the board, analog, it gets a bit, you know, it's still analog up to it hits the ADC hybrids here, and then it goes digital. And of course, 3.3 volt rail is going to be used for digital. It's not going to be used for your ADCs and front end typically. So, you know, something around here, and then you're going to get 3.3 volt rails over on your memory modules over here as well. But as you can see, they've got no bulk capacitance. They've got no bulk capacitance down on there because all the bulk capacitance is localized on the memory expansion board down in there. So they've just got a couple of ceramics, and it could certainly be a ceramic, for example, failing. I wouldn't completely rule it out, but you've got to go with the odds when you're troubleshooting stuff like this. And yeah, I don't know. I'm going to play around with that and give it a few extra little wiggles and pokes and see if I can get it to do something consistent. Now, I've probed a lot of the circuitry around here, and as you can see, there's not much in the way of bulk capacitance on here, just a few little tantalums around this shield here. And all of this seems to be running from the 5 volt rail, because if we go down, you can actually you know, measure the 5 volt rail on the pins of these chips, for example. Oh, sorry, you can't see the multimeter there, but it's showing a short, which indicates shorted to the 5 volt. Well, you know, as it should be. It's connected to the 5 volt rail. So all this sort of stuff seems to be 5 volt operated, with a 3.3 volt rail being used on possibly the memory modules here, I would suspect, and at least one of the pins on these ASICs under here. So I can actually prove that the memory modules, let's plug that in, and I'm guessing this would be 3.3 volt logic as well. And yep, it is. There's our 0.17 ohms. So you can see it's higher than what we've been getting, because it has to go through the contact resistance of the connectors and stuff like that. And you can see why the 1 milliohm is important here. If we were trying to do this with anything less, like a 10 milliohm resolution meter like the Fluke 87, we'd be really pushing the proverbial brown stuff up a hill with a pointy stick or a pointy probe. So I'm having a bit of a hard time tracing this thing down. It seems a bit non-consistent. So there seems to be some sort of possibly physical manifestation of the short, which is not uncommon to you know, vary with time and pressure and you know, flex and all sorts of stuff like that on the board. So really, it's almost gotten to the point where, well, I know that there's 4 tantalum caps here, and you know, I would always start out suspecting caps, and I can't find any electrolytics on the board that are doing that. So I think probably, even at this early stage in the tracing process, I think I might just go bugger it. I'll get the iron out and just suck off those 4 tantalums and, well, see if we get lucky. I don't think we will, but it's worth a shot. Only takes a minute. And of course, I was a bit off there. There's actually 2 caps on the 3.3 volt rail on each of those channels, except this one over here. And of course, getting these caps off is pretty trivial. You get your 2 irons, of course. I've shown this before, with your wedge tips on them, and get in there and bang, and it's straight out. Piece of cake. And of course, what are our odds of that being the issue? I reckon Buckley's and Murphy's, Buckley's and Murphy's. Yep, 0.15 ohms. Bugger. But maybe there's one good part about sucking out those caps. Let's put that back on our manual range. Is that we now have some really nice pads we can get down there with a lot of force. And look, I'm wiggling those probes, and look, 0.156. So you can tell 158, so you can 159, it's climbing. So by wiggling those probes around, you can tell that that contact resistance is pretty good. So we're getting 0.158 on that channel, 0.156, so it's gone lower. Let's check the cap next to it. 0.151, ooh, right next to it, really. 0.152. Oh, okay. They're actually connected via vias, like on long, looks like on long traces right down there. They're not a particularly low impedance path down there. 0.152, so we're getting lower, and all the way over here, 0.158, look at that. So is that consistent with this one? Okay, you see how that's higher. These two are higher than this one here. So that indicates like that it's this area in here perhaps, or you know, equidistant. The short is equidistant between those. So let's do that repeatedly. 0.160, jump up to channel 3, we'll call it. 152. Sorry, 154 that was, wasn't it? And this one seems to be the lowest, 0.148. So there you go. That one is, and this one should be slightly higher again. 0.1, oh no, 52, oh bloody hell. It's all over the shop. This is really embarrassing. Let's go up to the main connector up here. And, oh geez, there's not much in it, but that is sort of sticking out a little bit. Now I found and marked red here, I found 7 other ceramic caps which are on the 3.3 volt rail, and well really we could keep sucking these off until the cows come home, or we can go to plan B, which is actually some people's plan A for shorts like this, is hook it up to a high current power supply and see if we can blow the arse out of it. So what we're going to do here, I've got my big 40 amp power supply, set it to 3.3 volts, it's showing 3.2 volts on there, it's a smidge under, and it's capable of very high current. I've got some very thick, well quite thick leads on it, and I'm just going to apply this over the 3.3 volt rail. Be sure, if you're going to do this, make sure you get the right polarity of course, otherwise you're going to blow your board up. So now, the idea of this is that a couple of things could happen. One, you're going to heat up and blow that short out, so that then you will get that visual, hopefully, you know, it'll smoke or it'll warp, deform, catch on fire, whatever, you'll get that visual indication of the exact component that's actually failed. Or you could actually blow it and then blow it open and your short's gone. Well, that's not so bad, because you may blow it without any visual indications, and if you do that, then well, your board, you get your board powered back up again, but that chip or that cap or that part of the circuit that was failed has, you know, is not going to work. So then you're, you know, back to square one, almost troubleshooting, except you're not tracing a short anymore, you're tracing a you know, a failed component. So, you know, nothing can happen, of course. It's, you know, it could just heat up and you may not be able to find it. You may have to go over with your finger, try to find stuff that's hot, or maybe a thermal imaging camera if you're really fancy equipped like that, or an infrared thermometer or something. You might be able to find the hot spot. But I'm just going to touch these terminals down in there, and I'll try and do this, and we'll see what the current peaks up to. So let's give it a go. So hopefully, here we go, I don't get this wrong. So I've got my black going to the negative. Make sure you don't want to blow the board up. 1, 2, 3, 4, 5, 6. So that's our ground point, and then our second pin, here we go. 11 amps. Woohoo! Something is going to be smoking. That's a lot. That's a lot of amps. So, I don't know. Can't smell anything yet. This is why you need a heavy-duty power supply. So, no, it's 11 amps, and well, now I can just whip that off, turn it off, and maybe no, nothing. That's a bit of a bummer. Not entirely conclusive, except for the fact that it's a solid, whatever it is, it's a very solid short. Now, I think the power supply in this scope is, I think, rated for about 6 amps on the 3.3 volt rail. So it's rated for half that. So it's certainly not just the circuitry powered up. But anyway, let's see. Let's measure our resistance again and see if we haven't blown that thing out. No, we're still 0.16 ohms. There you go. Bummer. So anyway, we do have a very solid short somewhere in this thing. So I may have to leave it powered up a bit longer and, I don't know, maybe try and find a hotspot. Now I've got some physical connectors in there now, so I can leave these permanently hooked up, and I can start, there we go, I can feel that warm. That chip down there is warming up. That one's warm. Yeah, they're all warming up. So these chips are all powered up. I don't know, I guess I just leave it for a while and see which one. I mean, you know, that is chewing a lot of power there, so, you know, it's chewing in the order of like, you know, 35 watts or something. So it's a fair amount. So I might leave this and see if there's any visual indications. Well, I've checked the temperature on all 4 of these heat sinks, and they're all identical. So it's not like there's one chip different and you'd go, aha, that one's getting twice as hot as the others, you know. So I don't know if that's their normal operating temperature. They're in the order of 65 to 70 degrees or something like that. I mean, this thing takes a lot of power anyway. I'm not sure if that's normal. The other service manual I had said, as I said, the 3.3 volt rail was 6 amps capable or something like that. So, but it seems to be drawing, you know, in the order of 11 amps, 35 odd watts, and of course nothing else is getting warm at all. These main hybrid ADCs here, which ordinarily get very hot as well, aren't, and none of the circuitry over here. So as I measured before and suspected, that none of this is operating on the 3.3 volt rail. You know, none of the front end, nothing like that seems to be operating. So it's only these 4 devices here plus the expansion memory. Oh, and of course the if I plug the CPU board in there as well, the CPU might be taking some 3.3 volt as well. But I've had this thing going for about 5 odd minutes now, and well, nothing's smoking yet. Bummer. And of course, if the power supply in the unit was only rated for 6 amps on the 3.3 volt rail, then that would explain why it's shutting down, and this one is powering it just fine, because the 3.3 volt rail actually wasn't, you know, working. It had actually shut down. All the rails had, all the other rails had stayed up, and they were spot on, but the 3.3 volt rail was dead. So yeah, maybe that power supply was going into you know, some sort of current limit mode or something like that, and it just wasn't capable of supplying. Whereas this beastie will go up to 40 amps, no problems at all. So it'll, you know, power practically any load you give it, which is why it's still sitting on 3.3 volts. So given that all 4 of these chips here are getting to equal temperature, it shows that they're probably good, and you know, there's nothing you know, wrong or blown inside those chips at all. Potentially, you know, not 100% sure, but it's, you know, a reasonable guess that that is the case. So I guess all that's left, really, if I think that this is the only part of the 3.3 volt circuit, is to possibly find every darn cap on there and rip the damn things out. Oh, what a pain in the ass. Now, I'd like to load test the power supply just as a matter of course. I was going to use my dummy load, but then I looked at the manual, and the power supply, at least on the M model, I assume it's the same for this C model as well, that the 3.3 volt rail comes off the 14 amp capable 5 volt rail there. So you know, you really have to sort of load down both of them to check that it's actually capable of doing that. And I've plugged it back in here, and yes, the 3.3 volt rail is still dead. So whereas all the other rails are just fine, really. So we're only getting, you know, there's like 0.03 volts on the 3.3 volt rail, and the 5 volt rail is just hanging in there just fine and dandy. Well, as a matter of course, I did suck off every bypass cap on all of these channels on the 3.3 volt rail, and no, didn't find it, of course. We're still getting 0.16 ohms or thereabouts. And really, I mean, am I chasing a red herring here? I'm not 100% sure that I'm not, but you know, it seems likely, because that is an incredibly low resistance for a power rail, and of course you power it up and it's drawing double what the manual says it, you know, that the power supply is even capable of on that rail. So geez, what's left? I mean, I may have missed the odd bypass cap on here, but I'm pretty sure that the 3.3 is only around these 4 chips here, plus the memory interface expansion connectors here. And I've measured lots of places elsewhere on the board, and I cannot find the 3.3 volt rail going anywhere else. So, oh man, all that's left are these chips, I suspect, unless there's something else going on. Oh, I don't know, running out of time here. Well, unfortunately, that is it for the day. I got to head off, but I hope you enjoyed that little troubleshooting exercise anyway, even though we didn't get the happy ending we wanted. Sorry, not all these things work out. So, yeah, if you want to discuss it, jump on over to the EEVblog forum. If you've got any good ideas, of course, please do let me know. And yeah, sorry, these things aren't always easy. They do actually take time. What did I spend on this? Like an hour or something, and I have, you know, eliminated quite a few things, but yeah, we're still stuck. Something is going on. I don't know. Anyway, that's real life. Catch you next time.